The universe has a secret axis, and it should not exist. This hidden direction is buried within our most ancient map of the cosmos, the cosmic microwave background, the faint afterglow of the Big Bang itself. Its discovery defies a core rule of physics, the idea that the cosmos has no center and no preferred direction. By the end of this journey, you will understand the startling theories that attempt to explain this cosmic flaw, from multiverse collisions to cracks in the Big Bang theory. Why would the largest structures in existence align with our tiny solar system? And what does this say about our place in the cosmos? What does it mean if the universe itself is not what we thought 380,000 years after the universe began? A profound transformation occurred. For the first time, the cosmos cooled enough for light to break free from a dense, hot fog of particles. This moment of liberation created the very first cosmic photograph, a snapshot of the infant universe that has been traveling through the expanding void ever since. We call this ancient light the cosmic microwave background. It is a faint whisper of radiation that permeates every cubic inch of space, a relic from a time before stars, before galaxies, before anything we would recognize today. Its discovery in 1965 was a happy accident when two radio astronomers heard a persistent, mysterious hiss from every direction they pointed their antenna. They had stumbled upon the afterglow of creation itself. This glow is the cornerstone of modern cosmology, the single strongest piece of evidence we have for the Big Bang. By studying its incredibly subtle variations in temperature, we can measure the universe's age, its composition, and its ultimate fate. It is our most powerful time machine, offering a direct view into the universe's first moments. Yet within this seemingly uniform sea of light, there are strange ripples and patterns that defy easy explanation, pointing toward a deeper, more fundamental mystery hidden in its fabric. But as scientists refined their maps of this ancient light, a few strange features began to emerge. One of the most puzzling was the cold spot, a vast and unusually frigid region in the cosmic background. This area is not just a little bit colder, it is a colossal void of cold in a sea of subtle warmth, so large and so distinct that it defied easy explanation. It was as if someone had taken a cosmic ice cube and pressed it against the first photograph of the universe. Alongside this chilling anomaly, broader maps revealed a more unsettling pattern, a strange lopsidedness in the universe's temperature. One half of the sky appeared slightly warmer on average than the other half. This was not the random, even distribution that the cosmological principle demanded. The cosmological principle is the bedrock idea that the universe on the largest scales should look the same in every direction, with no center and no edges. It is the reason we do not believe we occupy a special place in the cosmos. Yet here was evidence of a fundamental asymmetry, a universe that seemed to have a preferred direction after all. These irregularities, first detected with startling clarity by satellites like the Wilkinson Microwave Anisotropy Probe, or WMAP, planted the first seeds of profound doubt. They were the quiet whispers that something in our foundational model of the cosmos might be deeply wrong. The search for a deeper, more systematic pattern had officially begun. The most shocking pattern, however, was not a spot or a general lopsidedness, but a direction. As researchers, particularly those working with the Wilkinson Microwave Anisotropy Probe, delved deeper into the data, they noticed something that sent a chill through the world of cosmology. The largest patterns imprinted on the cosmic background, the fundamental ripples that define the very structure of our universe, were not randomly oriented. Instead, they appeared to be aligned, They were all pointing more or less along a single, specific line through space. This was an axis, a preferred direction that the entire cosmos seemed to be whispering about. The statistical odds of this happening by pure chance were astronomically low. It was so unexpected and so philosophically unsettling that scientists gave it a name filled with dark humor, the axis of evil. The name was a deliberate provocation, a nod to how this single line in the sky seemed to undermine the most sacred principle of modern cosmology. It suggested the universe was not the same in all directions after all. It hinted that we might, against all odds, be looking at a center, or at least a fundamental skew in the fabric of reality. This discovery forced a painful question upon the scientific community. Were they simply seeing a one-in-a-million statistical fluke, a ghost in the machine, or were they staring directly at a genuine crack in the very foundation of the Big Bang theory itself? To capture this ancient whisper, we must build the quietest ears in the universe, on the high, dry plateaus of the Atacama Desert, and from the frigid emptiness of space, observatories like the Planck satellite listen. Their task is to measure the faint heat of the cosmic background, a signal so cold it is just a few degrees above absolute zero. But the real challenge is not the cold, it is the variations. The satellites are hunting for temperature differences of mere millionths of a degree across the entire sky. It is the cosmological equivalent of trying to measure the heat from a single candle on the moon while standing on Earth. These instruments must be shielded from the heat of the sun, the warmth of the Earth, and even the faint infrared glow of dust in our own solar system. Every possible source of noise is painstakingly mapped and subtracted, leaving only the pristine, primordial signal. Once we have this impossibly detailed map of hot and cold spots, the real work begins. How do you make sense of a sky full of random-looking splotches? Scientists use a mathematical language of patterns called spherical harmonics. Think of it like this. If you listen to a complex chord of music, you can break it down into its fundamental notes, its bass, its treble, and every frequency in between. The cosmic microwave background is that chord, a single, frozen note from the beginning of time. By applying spherical harmonics, we break this note apart. We separate the universe's deep bass, the largest ripples that stretch across billions of light years, from its higher-pitched treble, the smaller, more intricate wrinkles. This breakdown is called the power spectrum, and it is the Rosetta Stone of cosmology. It tells us the precise recipe of the universe, how much dark energy, dark matter, and ordinary matter it contains. It was by staring at this decomposed map of the universe's deepest notes that researchers saw the impossible. The largest waves, the fundamental bass notes of creation, were not playing at random. They were all in tune, all vibrating along the same cosmic axis. The data was too clean, too structured. The alignment was not a blur in the raw image. It was a clear, mathematical signal emerging from the most sophisticated analysis possible, a ghost in the machine that refused to disappear. The breakdown of the cosmic background into its fundamental notes reveals the next layer of the mystery. The largest of these notes, the deep bass of the universe, are known as the quadrupole and the octupole. The quadrupole is the simplest shape beyond a uniform sphere, representing a basic elongation, a kind of cosmic football stretching across the sky. The octupole is the next most complex pattern, a cloverleaf structure with alternating hot and cold lobes. These are not small features, they are the most immense ripples in the fabric of space-time, patterns so vast they define the distribution of galaxies. The shocking discovery was not just that these two separate patterns were aligned with the infamous axis, but that their alignment was eerily synchronized. The plane of the quadrupole's elongation and the plane defined by the octupole's lobes were not random relative to each other. They were lined up. It was as if two different musical instruments, one playing a deep, resonant hum and the other a more complex chord, were both vibrating on the same exact stand. This alone was a statistical nightmare, a 1 in 1,000 fluke that refused to vanish from the data. But the true blow to our cosmic world came from the direction of this shared alignment. The plane of these gargantuan patterns, the largest things we can measure, points directly along the ecliptic plane of our own solar system. The ecliptic is the flat disk in which Earth and all the other planets orbit the Sun, our tiny, local celestial neighborhood. The profound improbability of this correlation is staggering. Why would the fundamental architecture of the entire observable universe, imprinted at the moment of its birth, share a preferred orientation with the orbital plane of our little planet? It is a coincidence that feels deeply wrong, as if the universe's blueprints were somehow aware of our existence. This directly challenges the Copernican principle, the foundational idea that we do not occupy a privileged or central position in the cosmos. The axis of evil is not just a curious alignment in the distant heavens, it is an alignment that seems to point disturbingly back at us. This alignment is so improbable it forces a painful choice upon scientists. Are we seeing a genuine crack in our model of the universe, or are we simply the victims of a cosmic statistical illusion? The central battleground in this debate revolves around a concept called cosmic variance. Because we can only observe one single universe, our map of the cosmos is fundamentally limited. We have no other universes to compare our own against. Imagine you could only ever meet one person in your entire life. If that person had green hair, you might assume everyone in the world has green hair. Cosmic variance is that same principle applied to the largest scales of reality. The patterns we see in the cosmic microwave background, especially the very largest ones like the quadrupole and octupole, are the ultimate sample size of one. There is only one universe's worth of these giant ripples to study. It is entirely possible, though statistically unlikely, that our particular sky just happens to look lopsided by pure random chance. This is the skeptical scientist's preferred explanation, that the axis of evil is a ghost in the data, a mirage created by our limited viewpoint, yet the numbers themselves push back fiercely. Calculations show that the specific alignment of these largest patterns and their eerie correlation with our solar system's plane has a probability of less than 1 in 1,000 of occurring randomly. In most other fields of science, that would be considered a definitive discovery, but in cosmology, where the foundational principles are so sacred, the standards for proof are almost impossibly high. This tension defines the modern quest to understand our cosmos. Do we dismiss this profound anomaly as mere noise, upholding the elegant simplicity of our theories, or do we accept it as a signal, a clue that our universe is far stranger than we ever dreamed? This debate is not just academic, it is what drives the construction of ever more powerful telescopes and satellites, all listening for the next whisper from the void, hoping to finally distinguish a cosmic conspiracy from a cosmic coincidence. The Planck satellite arrived with the promise of clarity. Launched by the European Space Agency, it was the most advanced cosmic ear ever built, designed to listen to the universe's first whisper with an unprecedented sensitivity. Its mission was to map the cosmic microwave background in such exquisite detail that it would either erase the anomalies as mere ghosts in the machine or confirm them as features of reality. After years of painstaking data collection and analysis, the verdict arrived. Planck did not make the axis of evil disappear. Instead, it gave the anomaly a sharper, more defined form. With its superior resolution and its meticulous efforts to subtract foreground noise from our own galaxy, Planck confirmed the strange alignments in the universe's largest patterns. It ruled out many potential instrumental errors that had haunted previous missions, tightening the noose around conventional explanations. While the satellite's incredible precision did reduce the statistical significance of some of the other peculiarities, like the precise nature of the cold spot, the coordinated alignment of the low-order multipoles, the quadrupole and octupole, remained stubbornly present in the data. This was no longer just a strange reading from one telescope. The universe's preferred direction had been confirmed by two independent, world-class instruments. The axis of evil was thus transformed. It evolved from a curious and debatable oddity in the WMAP data into a persistent, refined problem etched into our most precise map of the cosmos. It was now a feature of our universe that actively defied explanation, a quiet rebellion against the cosmological principle that could no longer be ignored. The question shifted from whether the alignment was real to what kind of physics could possibly account for it. Yet a third clue deepens the mystery, one that touches the very texture of the cosmic background. Across the sky, the fluctuations in temperature are not spread with an even hand. One entire hemisphere of the universe appears to have slightly more powerful, more pronounced temperature variations than the other. Imagine a master painter carefully applying the final texture to a vast spherical canvas. Now picture that for some reason, the brushstrokes on one half of the sphere are consistently bolder, more dramatic, and more varied than the strokes on the other half. This is the essence of the hemispherical power asymmetry. The universe is not just aligned along an axis, it is also textured differently from one side to the other. This is another form of directional preference, a cosmic lopsidedness that compounds the puzzle of the axis of evil. It suggests that the initial conditions of the universe, the very first moments of the Big Bang, may not have been perfectly uniform after all. Perhaps the seed of creation itself contained a fundamental twist, an inherent skew that was baked into the fabric of space-time and then stretched to cosmic proportions. Why would one half of reality be born with more potency than the other? This asymmetry challenges the very idea of a smooth, featureless beginning, pointing toward a far more complex and perhaps even personalized origin story for everything we see. For a theory to be considered the bedrock of modern cosmology, it must be incredibly successful, and the Lambda-CDM model is exactly that. It is our standard picture of the universe, a beautifully simple and powerful framework that explains the cosmos's expansion, the existence of dark energy, and the formation of galaxies with astonishing accuracy. Yet this entire model rests upon one fundamental assumption, that the universe is homogeneous and isotropic, meaning it looks the same in every direction and from every location. The Lambda-CDM universe has no center, no edges, and certainly no preferred axis. This is why the axis of evil is so much more than a statistical oddity. It is a direct and profound challenge to the very foundation of our cosmic understanding. If the universe truly has a preferred direction, then our standard model, for all its successes, is incomplete. We are forced to peer beyond it, into the realm of speculative and extraordinary new physics that could explain why our cosmos is not the same in all directions. One possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, is not perfectly uniform. Perhaps it is anisotropic, meaning it exerts a slightly different pressure along one specific direction. This would create a subtle tug on the fabric of space-time, a kind of cosmic wind that could have imprinted a directional preference on the infant universe, leaving its mark on the cosmic microwave background. Another idea involves the influence of primordial magnetic fields. These would be unimaginably powerful fields generated in the universe's first instance, whose lingering influence could have stretched and aligned the largest structures, like a cosmic comb smoothing spacetime in one preferred direction. The most radical proposals even suggest modifications to Einstein's theory of gravity itself. Perhaps gravity does not work exactly as we think on the very largest scales. Theories that introduce new vector fields, directions woven into the force of gravity, could naturally produce a universe with a built-in axis. Each of these ideas is a potential key to a deeper reality, a set of laws that operated in the first fleeting moments after the Big Bang, laws we can no longer see directly but whose signature might be written in the sky. The axis of evil, therefore, is not a flaw to be erased from our maps but a potential gateway. It is a faint signal from an era of physics we have not yet discovered, a whisper from a time when the rules of reality were being written. The most successful theory we have for the universe's first moments seems to be failing its most basic test. Cosmic inflation was proposed to solve fundamental problems, explaining why the universe is so large, so flat, and so uniform. The idea is both simple and staggering. A fraction of a second after its birth, the universe underwent a violent, exponential growth spurt, ballooning from a subatomic speck to a vast cosmos in less time than a single heartbeat. This incredible stretching would have ironed out any initial wrinkles, smoothing the cosmos into the nearly homogeneous state we see in the cosmic background. But the axis of evil is a wrinkle that inflation was specifically designed to erase. Its persistence suggests that the initial conditions of the universe were not so simple after all, that the smoothness we observe might be a local illusion in a far more complex and textured reality. Could inflation itself have been the source of this cosmic directionality? The standard model of inflation is isotropic, stretching space equally in all directions, like a perfectly round balloon inflating. But what if, in its earliest moments, the inflationary energy was not a uniform field but had a built-in directionality, a kind of cosmic grain? Anisotropic inflation is a theoretical possibility where space stretched faster along one axis than others. Think of pulling on a piece of taffy. It elongates more in the direction you pull, developing a distinct grain and internal alignment. If the universe underwent such a directional stretch, it could have imprinted a preferred axis onto the fabric of spacetime, a fossil memory of its own violent birth that survives in the alignment of the largest cosmic patterns. This would mean the very mechanism created to enforce uniformity was, in fact, fundamentally lopsided. Alternatively, the axis might be a relic from a time before inflation even began. Perhaps the pre-inflationary universe was not a perfectly symmetric, featureless point. It could have possessed its own complex geometry, perhaps a crystalline structure or a fundamental spin inherited from some deeper physics we do not yet understand. Inflation would have then magnified this initial imperfection, blowing it up to a cosmic scale and freezing it into the cosmic microwave background for us to find billions of years later. The axis would then be a window into a realm we can never observe directly, a glimpse of the universe's true initial state before the great smoothing began. This mystery places immense pressure on the simplest, most elegant models of inflation. A single, smooth inflationary field cannot easily account for such a stark directional preference. This has forced cosmologists to explore more complex, and some would say less elegant, scenarios involving multiple fields of inflationary energy interacting with one another. In these multi-field models, the collapse or collision of different fields could create directional tensions, twists in the fabric of spacetime that leave a permanent scar on the cosmos. The axis of evil, therefore, is not just a puzzle to be solved, it is a powerful guide. It tells us that our universe's origin story is likely more intricate, more nuanced, and perhaps even more beautiful than the simple, smooth beginning we once imagined. Perhaps the most unsettling correlation is not just the existence of an axis, but where it points. This cosmological line of evil is not oriented toward some distant, anonymous void. It aligns with the ecliptic plane of our own solar system, the flat disk in which Earth and the other planets orbit the Sun. It also traces the direction of the Sun's own journey as our star moves through the galaxy at a staggering speed. This is a coincidence that feels deeply wrong. Why would the largest possible structures in the entire cosmos, patterns imprinted at the universe's birth, share a directional preference with our tiny, local neighborhood? It is as if the blueprint for a continent were mysteriously aligned with the footprint of a single house built upon it. This correlation strikes at the heart of the Copernican principle, the foundational idea that we do not occupy a privileged place in the universe. The axis seems to be pointing directly back at us, suggesting a connection between the global universe and our local cosmic address that, by all rights, should not exist. The immediate and most scientifically conservative explanation is that we are seeing a ghost in the machine. Perhaps our efforts to clean the data, to subtract the foreground glow of dust within our own solar system, are imperfect. This dust, concentrated in the ecliptic plane, could be leaving a faint residual signal that mimics a cosmological axis. It is the ultimate contamination, a smudge on our lens that just happens to look like a fundamental feature of reality. Alternatively, our motion through space could be casting a longer shadow than we anticipated. The Sun's movement creates a Doppler effect, a stretching and compressing of the cosmic microwave background light that we must carefully correct for. If this correction is even slightly off, it could introduce a false directional bias into the map. These possibilities offer a comforting escape, a way to preserve our standard model of an isotropic universe by blaming the anomaly on a local, mundane effect. Yet, despite exhaustive efforts by the Planck team and others to model and remove every conceivable source of local interference, the alignment persists. It stubbornly refuses to be cleaned away. If this is not an error, then the implications are staggering. It could mean that our motion is not just a local phenomenon, but is somehow coupled to the large-scale flow of the universe itself. We might be caught in a vast cosmic current, a river of spacetime that stretches back to the beginning of everything. Or it could hint at something even more profound, that the very structure of reality has a grain to it, a fundamental anisotropy that links the infinitesimally small to the impossibly large. The axis forces us to ask a question we thought science had settled centuries ago. Are we, in some strange and unexpected way, special after all? This painstaking search for contamination begins with the vibrant foreground of our own Milky Way. Our galaxy is not a silent, dark window to the cosmos beyond. It is a brilliant and noisy neighbor. Its light comes in several distinct forms that must be meticulously mapped and peeled away. There is the gentle glow of interstellar dust, tiny grains warmed by starlight and radiating at the same microwave frequencies as the ancient cosmic background. Then there is the sharp crackle of synchrotron radiation, emitted by electrons spiraling at nearly the speed of light through the galaxy's magnetic fields. A third source, free emission, arises from electrons scattering off atomic nuclei in hot galactic gas. Each of these foregrounds paints a complex, swirling pattern across the entire sky, a brilliant veil obscuring the faint primordial whisper behind it. To see the true cosmic background, scientists must become master art restorers, carefully removing these overlaid paintings without damaging the priceless, ancient canvas beneath. They do this through a process called component separation. Since each type of foreground light has a unique spectral signature, a specific way its intensity changes across different microwave frequencies, powerful satellites like Planck observe the sky not just once, but at 9 separate frequencies. It is the difference between looking at a painting under a single white light and examining it under 9 different colored lights. Under each colored light, certain layers of the painting become more or less visible. By comparing these 9 different views of the sky, sophisticated algorithms can identify the fingerprint of galactic dust, the distinct signature of synchrotron radiation, and subtract them. What remains, in theory, is the pristine signal of the cosmic microwave background. Researchers have subjected this cleaned map to the most brutal tests imaginable. They have created hundreds of different simulated skies, injecting known foregrounds, and then applying their subtraction techniques to see if the process itself artificially creates a preferred axis. They have varied their models of galactic dust, testing extreme assumptions about its composition and distribution. They have even analyzed the cleaned data using multiple, independent methods developed by competing teams around the world. The result is always the same. No matter how they slice the data, no matter which model of the galaxy's glow they use, the alignment persists. The axis remains etched into the cleaned map with a stubborn clarity. This exhaustive process of elimination makes a purely local explanation increasingly difficult to sustain. If the axis were a mere ghost from our galaxy, it should have faded or shifted as the models of that galaxy were changed. The fact that it withstands this forensic scrutiny points its origin beyond our local neighborhood toward a deeper cosmological truth. The signal is not coming from our backyard, it is a whisper from the edge of time itself. The search for an explanation leads us to the very edge of theoretical physics, to a concept so radical it challenges our perception of dimensionality itself. Imagine the universe as a cosmic hologram, the world you see and feel in 3 rich dimensions, from the depth of a canyon to the height of a mountain, might be nothing more than a magnificent illusion, a projection of information stored on a distant, 2-dimensional surface. This is the holographic principle, an idea born from the strange physics of black holes and the complex mathematics of string theory. It proposes that all the information describing every star, planet, and person could be encoded on a vast cosmic boundary, much like the data for a 3-dimensional movie is stored on a flat 2-dimensional Blu-ray disc. In such a reality, our perceived 3-dimensional existence is a kind of grand decoding, a projection from a more fundamental, lower-dimensional reality. How could this possibly explain the axis of evil? If our universe is a projection, then the projection process itself might not be perfectly isotropic. The underlying 2-dimensional information screen, the foundation of everything, could have its own inherent grain or structure. A fundamental anisotropy in this foundational layer, a slight directional preference in how the information is stored or processed, would then be projected upward into our 3-dimensional world. The preferred axis we see in the cosmic microwave background could be a ghostly echo of that deeper 2-dimensional structure, a permanent scar from the projection process that has been visible since the universe's first light. The cosmic microwave background would then be more than a relic. It would be the foundational code of our holographic universe, and the axis would be a line written directly into that code. This idea remains deeply speculative, a frontier of thought not yet supported by experimental proof. Yet its very consideration reveals the profound impact of the axis of evil. It is not merely a puzzle to be solved within our current models. It is a force that is pushing cosmologists to question the most fundamental nature of reality. The anomaly compels us to ask if the universe is ultimately a construct of information, and if the laws of physics as we know them are merely emergent properties from a deeper, two-dimensional truth. Far beyond the temperature map of the infant universe, another ghost is moving in the darkness. Astronomers have observed a strange and relentless current in the cosmos, a vast river of galaxy clusters all streaming in the same direction. They call this the dark flow. It is as if an immense, unseen hand is pulling thousands of galaxies toward a point beyond the edge of our observable horizon. This motion defies the smooth, uniform expansion predicted by our standard model, where on the largest scales, everything should be moving apart in a stately, homogeneous drift. The dark flow suggests a colossal bulk motion, a coordinated drift on a scale so immense it hints at something monumental existing outside our cosmic bubble. What could possibly exert such a profound gravitational pull on so much matter? The answer might be intimately connected to the axis of evil. Some theorists propose that both phenomena, the temperature alignments in the ancient light and the coordinated motion of modern galaxies, share a single, spectacular origin. Imagine the infant universe in the first fleeting instance of inflation, being subtly tugged by the gravity of something unimaginably vast. This could have been a pre-inflationary structure, a relic from a time before time, whose gravitational imprint warped the expansion, creating a directional preference that was frozen into the cosmic microwave background as the axis of evil. But as the universe evolved, that same gravitational source, still lying beyond our sight, continued to pull. It would have set entire superclusters of galaxies into motion, creating the dark flow we detect today. This single explanation binds the first light of creation to the present-day dynamics of the cosmos. An even more radical idea suggests the source is not a structure, but an entire other universe. In a multiverse scenario, our universe is one bubble among countless others in a frothing, eternal cosmic sea. The gravitational influence from a neighboring universe bubble, brushing against our own in the hyper-realm of the multiverse, could have tugged on our cosmos from the outside. This external pull would have imprinted a direction on our space from the very beginning, creating the axis, while its ongoing influence would still be herding galaxies in a coherent stream billions of years later. This transforms the axis of evil from a mere curiosity into a potential signpost. It points not just to a direction in space, but to a deeper, interconnected reality where the largest imbalances we observe in both light and motion are threads leading back to a single, extraordinary source. The secret axis may be the first clue in a much larger story, one that connects the first whisper of heat to the silent, flowing rivers of the dark. Another thread in this cosmic tapestry leads us back to a force we know intimately: magnetism. While we think of magnetic fields as guiding compass needles or holding notes on a refrigerator, their primordial cousins could have been architects of the universe's largest structures. Imagine a magnetic field not confined to a star or a galaxy, but one that stretched across the entire cosmos in its first second of life. Such a primordial field would have been woven into the fabric of spacetime itself, a fossil from an era of physics we can no longer directly probe. As the universe expanded and cooled, this all-pervading field would have interacted with the dense, seething plasma of charged particles that filled the early cosmos. Charged particles, like electrons and protons, cannot cross magnetic field lines easily. They spiral around them. This simple fact could have been the engine of anisotropy. In regions where the field lines were denser or more aligned, the hot plasma would have experienced a subtle directional pressure, a kind of cosmic push that was stronger in one direction than in others. This pressure would have gently sculpted the density fluctuations in the primordial soup, guiding the collapse of matter and the propagation of sound waves in a preferred direction. The result would be a universe whose very first ripples, the ones imprinted on the cosmic microwave background, carried the memory of that magnetic grain, a faint but measurable alignment along the field's original orientation. This is a profoundly appealing idea because it uses a known, conventional physical mechanism to break the universe's symmetry. We understand how magnetic fields work, and we know they can create directional effects. The axis of evil in this light would not be a sign of radical new physics, but a consequence of a powerful, ancient magnet imprinted on the sky. The challenge, however, is monumental. Generating a magnetic field on a cosmological scale is no small feat. In the modern universe, magnetic fields are generated by dynamos, the churning motion of conductive fluids inside stars and galaxies. But to create a field that fills the entire cosmos, you need a mechanism that operates before any stars or galaxies existed, in the first fleeting instance after the Big Bang. Some theories point to phase transitions in the early universe, moments when the fundamental forces of nature split from one another. These cosmic rearrangements could have released immense energy, creating turbulent shocks that generated magnetic fields. Other ideas involve the inflation field itself, suggesting its quantum fluctuations could have seeded these vast magnetic structures. Yet, the required strength and coherence of such a field are difficult to achieve without fine-tuning the models. Furthermore, if such a powerful field did exist, it should have left other imprints on the cosmos, perhaps affecting the abundance of light elements or the formation of the first galaxies, traces we have not yet definitively found. So while primordial magnetism offers an elegant and physically grounded pathway to the axis we observe, it remains a compelling hypothesis waiting for its crucial piece of evidence, a discovery that would connect the force on your fridge to the deepest geometry of reality. This cosmic bruise could be a scar from a battle between universes. The multiverse hypothesis offers one of the most breathtaking explanations for the axis of evil. Imagine our cosmos not as a solitary creation, but as a single bubble floating in an infinite, frothing sea of other universes, each with its own distinct physics. This is the landscape of eternal inflation, a reality where new universe bubbles are constantly budding off from an eternally expanding background. In such a chaotic foam, collisions would be inevitable. Picture two of these colossal bubbles, each a complete universe, gently bumping into one another in the hyperdimensional void. The energy released at their boundary would be unimaginable. This collision would send a shockwave rippling through the newborn cosmos, a directional imprint that would persist for all time. The axis of evil, in this radical view, is not a flaw in our data but the fossilized boundary of that impact. It is the cosmic equivalent of a bruise on the skin of our universe, a permanent reminder of a time when we were not alone. The alignment we see in the ancient light would be the edge of the contact, the point where the physics of our universe met the foreign laws of another. This theory profoundly reframes the mystery. The axis is no longer a problem to be solved within our standard model, but a potential piece of evidence for something infinitely grander. It transforms a statistical anomaly into a cosmic artifact, a relic from beyond our observable horizon. Why would such a collision create a preferred direction aligned with our solar system? The answer is both simple and staggering. It would not. The alignment with our local space is a pure, breathtaking coincidence, a fact that makes the hypothesis both more compelling and more difficult to accept. If true, it means we are literally seeing the fingerprint of another universe, a ghost from outside our reality, forever frozen in the first light of our own. While this idea is currently beyond the reach of direct verification, it offers a tantalizing narrative. The secret axis buried in the cosmos may be the ultimate signpost, pointing not to a center but to a doorway. A sixth and deeply mathematical clue reinforces the others. On the very largest scales, the universe is far too quiet. The cosmic microwave background shows a surprising lack of correlation between points separated by more than 60 degrees across the sky. Think of it like this: if you were standing in a vast, open field on a foggy morning, you would expect the temperature and humidity in the air to be related over long distances. A patch of fog a mile away would tell you something about the patch of fog right above you because the atmosphere is a connected system. The standard cosmological model makes a similar prediction for the infant universe. The hot and cold spots in the cosmic background, even those very far apart on the sky, should show a statistical relationship, a faint echo of their common origin in the Big Bang. Yet when we measure it, that expected connection simply is not there. On the grandest scales, the temperature fluctuations seem to operate independently, as if the largest structures in existence are not talking to each other. This missing correlation is mathematically tied to the weakness of the quadrupole and octupole, those largest base notes of the universe that define the axis of evil. A universe that is smooth and random in its initial conditions, as our standard model requires, should have produced stronger large-angle correlations and more powerful low-order multipoles. Instead, we see a coordinated suppression. The universe appears unexpectedly lumpy and disconnected on its very largest canvases, failing to match the perfect Gaussian randomness that inflation was designed to create. This is not three separate puzzles, a strange axis, weak base notes, and missing correlations. They are three faces of a single, profound mystery. They point toward a common origin, a fundamental quirk in the initial conditions of reality that left the cosmos with a preferred direction and a startling silence in its deepest voice. The very laws that generated our universe may have contained a directional bias from their first moment, a flaw in the symmetry of creation that we are only now beginning to decode. The ultimate verdict on this cosmic axis will come from a new generation of eyes now being trained on the sky. From the high, thin air of the Atacama Desert in Chile to the pristine ice of the South Pole, a monumental leap in observational power is taking shape. Projects like the Simons Observatory and its even more ambitious successor, CMB-S4, are not merely upgrades, they are revolutions in our ability to listen. These facilities will deploy armies of detectors, tens of thousands of them, working in concert to capture the cosmic microwave background with a sensitivity we can barely conceive of today. Their primary mission is to see what we have been missing, to map not just the temperature of the ancient universe, but its polarization. Think of the CMB light as a wave rippling through space. Temperature tells us how hot or cold that wave is, but polarization tells us the specific direction in which that wave is wiggling. This polarization is a fossil imprint of the very last time that light bounced off an electron, 380,000 years after the Big Bang. It carries an independent and in many ways more pristine record of the universe's violent infancy. If the axis of evil is a true feature of the cosmos, a fundamental skew written into the laws of physics, then its signature must be etched into this polarized light as well. It would be like finding the same strange symbol carved into both the front and back of an ancient relic, confirming it was part of the original design and not a later scratch. These next-generation observatories will search for that exact confirmation. They will look for patterns in the polarization that align along the same mysterious axis, for a coordinated swirl in the universe's earliest wiggle that matches the temperature alignment. Finding it would be the smoking gun, the definitive proof that we are not seeing a ghost in the machine, but a real architectural feature of reality. It would instantly transform the axis from a curious anomaly into a hard data point that any successful theory of the universe must explain. Conversely, If these exquisitely sensitive maps find no such alignment in the polarization, the mystery of the axis of evil will likely fade. It would point overwhelmingly toward a complex statistical fluke, a one-in-a-thousand coincidence amplified by our limited view and the challenging process of cleaning foreground contamination. The future of cosmology hinges on this independent test. We are building the instruments that will finally let us hear the universe's first whisper in stereo, and in doing so, they will tell us if the silence we hear on the largest scales is a true feature of the cosmos or merely an echo of our own limitations. This discovery strikes at the deepest foundations of our cosmic worldview. For over 4 centuries, the Copernican principle has been the guiding light of science, the philosophical engine that pushed us from a universe centered on Earth to one where we are adrift on a tiny speck in an unimaginable vastness. It is the bedrock assumption that our position is not special, that the laws of physics are the same everywhere, and that any observer anywhere would see a universe roughly identical to our own. The axis of evil does not just challenge a scientific model, it confronts this core philosophical tenet head-on. What if, against all odds and expectations, we do occupy a peculiar place? What if the largest structures in all of existence, the very base notes of creation, are subtly tuned to the plane of our own humble solar system? This is not a return to a geocentric universe, but something potentially far stranger. It suggests a cosmos where the global and the local are unexpectedly linked, where the grand architecture of reality has a grain, and our tiny world is somehow oriented along that fundamental grain. The implications for humanity's self-image are staggering. It would force a radical re-evaluation of our place in the cosmos, not as the center, but as a point of peculiar alignment. Are we, by some impossible coincidence, living at the one spot where the universe's hidden symmetry becomes visible? Or does this axis point toward a deeper, more interconnected reality, one where our local frame of reference is not an accident but a consequence of a law we have not yet discovered? The philosophical shockwave is this: the universe may not be indifferent to our presence after all, and that is a thought more disruptive than any mere scientific revision. The whispers from the beginning of time are not the only signals pointing toward a cosmic direction. Far beyond the ancient glow of the cosmic microwave background, another clue emerges from the brilliant hearts of distant galaxies. Quasars are the most powerful and persistent engines in the universe, supermassive black holes at the centers of galaxies, devouring matter and shining with a ferocious light that can be seen across billions of light years. As this intense light travels through the vast, mostly empty space between galaxies, it can become polarized, meaning its light waves vibrate in a preferred plane. For decades, astronomers assumed the polarization directions of these quasars, scattered randomly across the sky, would average out to zero, revealing no overall pattern. The universe, after all, should have no preferred direction. Yet when researchers compiled the data from thousands of these beacons, a faint but startling signal appeared. The polarization axes of these quasars were not completely random. On the largest scales, they showed a subtle tendency to align with one another, and the direction of this vast cosmic grain, this coordinated whisper from across the universe, aligns eerily with the axis of evil. This is a connection that spans nearly the entire age of the cosmos. The cosmic microwave background is a fossil from the universe's infancy, just 380,000 years after the Big Bang. The light from quasars has been traveling for billions of years, a snapshot of a much more mature universe. For both to share the same directional preference means the anisotropy, the cosmic lopsidedness, is not locked in the distant past. It is a property that has persisted, a fundamental feature of spacetime that has influenced the journey of light for almost 14 billion years, Imagine you discover that every photograph from your family album, from your great-grandparents' wedding to your last birthday, has a faint, identical scratch running diagonally across the corner. You would not blame the individual cameras or the different photographers. You would suspect a fundamental flaw in the album itself, a grain in the leather or a warp in the binding that affected every picture placed inside. The alignment of quasar polarization with the CMB axis suggests that the universe itself is that album, and the axis of evil is that fundamental scratch in its fabric. This correlation, if definitively confirmed, would elevate the mystery from a curious anomaly to a pervasive law. It would mean that the vacuum of space is not perfectly uniform, that it has a subtle grain that twists the polarization of light traveling through it over cosmic distances. This would be a direct challenge to Einstein's principle of general relativity, which assumes the smooth isotropy of space. The universe would not only have a preferred direction imprinted at its birth, but it would still possess that direction today, guiding the very vibration of light from the most powerful objects in existence. The secret axis is not just a relic, it is an active and enduring feature of our reality. This ancient whisper of heat is the universe's first and most fundamental broadcast. Every subtle variation in its temperature, every faint ripple, is a piece of information encoded at the dawn of time, a message about the initial conditions that gave rise to everything we see. From this perspective, the axis of evil is not a flaw in the data, but a piece of that message we have not yet learned how to read. It is a paradox of information, a signal that our current models of cosmic genesis are simply not equipped to decode. Our standard theories are built on principles of perfect randomness and symmetry, expecting the universe's first message to be a form of white noise, a static hiss with no coherent pattern. Instead, we are receiving a signal with a distinct low-frequency hum, a persistent tone that suggests a deeper, more complex structure to reality. Think of it like tuning a radio and expecting to hear random static, but instead finding a faint, repeating melody buried in the noise. You would not assume the melody is an error in your receiver. You would realize you have stumbled upon a station broadcasting on a frequency you never anticipated. The axis is that melody, a clue written into the foundational code of the cosmos, pointing toward a physics we have not yet discovered. This anomaly encourages us to reframe the entire mystery. It is not a failure of our theories, but a guidepost. The universe is not broken. It is simply more intricate and perhaps more beautiful than our most elegant models have allowed. The alignment could be a hint of a deeper symmetry, one that is not simple and isotropic, but richer and more textured, like the grain in a piece of wood or the crystal structure of a diamond. Or it may point to a far more complex initial state for the cosmos, a beginning that was not a featureless point but a structured entity with its own inherent geometry and directionality. By listening to this persistent signal, we are being guided toward a more complete and nuanced understanding of creation, one where the first message from the beginning of time still holds secrets we are only beginning to grasp. Another profound possibility lies woven into the very fabric of spacetime, in flaws that formed as the universe cooled. When any material undergoes a radical change of state, like water freezing into ice, defects can naturally appear. The early cosmos experienced its own series of cosmic phase transitions, moments when the fundamental forces of nature split from one another. Theorists propose that during these violent rearrangements, exotic structures called topological defects could have been born. These are not mere scratches but stable, persistent wrinkles in the geometry of reality itself. Imagine the universe cooling like a vast, hot sheet of metal. As it contracts, stresses can cause it to buckle in specific, permanent ways. A cosmic string would be a one-dimensional defect, an infinitely long, unimaginably thin filament thinner than a proton yet possessing the mass of a mountain range per inch. It would be a flaw in spacetime so dense that its gravity would warp everything around it. A domain wall would be a two-dimensional sheet, a vast, impermeable membrane separating regions of space with different properties. Even more abstract are textures, not like configurations in the fields that permeate the cosmos. The crucial point is that all of these defects break the perfect symmetry of the universe by their very existence. A cosmic string, for instance, has a direction. It stretches across the cosmos, creating a massive, linear gravitational pull along its length. Any structure forming in its vicinity would feel this directional tug. If such a defect existed in the early universe, its anisotropic gravitational potential would have acted like a cosmic comb, gently guiding the density fluctuations of the primordial plasma to align along its orientation. The hot and cold spots in the cosmic microwave background would have formed in its shadow, inheriting its preferred direction as they froze into place. The axis of evil, then, could be the ghostly imprint of a cosmic string we can no longer see, or the faded gravitational memory of a domain wall that has since decayed. While dedicated searches for the direct signatures of these defects, such as telltale double images of distant galaxies caused by a string's gravitational lensing, have so far come up empty, they remain a compelling and physically plausible explanation. They represent a fossil from a more complex and textured early universe, one where the smooth perfection we expected was never truly there, and where the largest patterns we see today were sculpted by the enduring scars of creation. Our own motion paints the first and strongest stripe upon the cosmic map. The solar system is not sitting still, it is rushing through space at a staggering speed, and this movement creates a profound imprint on the cosmic microwave background known as the dipole. As we fly in one direction, the CMB light ahead of us appears compressed and blue-shifted, making it slightly hotter, while the light behind us is stretched and redshifted, making it colder. This temperature difference is the single largest feature in the entire sky, a clear and expected signature of our local journey. Scientists understand this effect perfectly, and they meticulously subtract it from the data, striving to reveal the pristine, primordial universe beneath. The immediate suspicion, then, was that the axis of evil was a ghost, a residual smear left by an imperfect subtraction of this colossal dipole. Perhaps a tiny, unaccounted-for fraction of our motion signal was leaking into the maps of the larger multipoles, artificially creating the illusion of alignment. Yet this comforting explanation has not held up. Researchers have subjected this process to excruciating scrutiny, using multiple independent methods to remove the dipole, and the axis remains stubbornly in place. It persists in the clean data, a pattern that is fundamentally separate from our local velocity. This forces a much more profound and provocative question. What if the relationship is not one of contamination, but of a common cause? Our motion through the cosmos is not random, it is a response to gravity. We are being pulled, the entire Milky Way, along with our local group of galaxies, is flowing toward immense concentrations of mass like the Great Attractor and the Shapley supercluster. This motion is our dipole. Now consider the gravitational forces that could have created the axis of evil, the vast primordial tugs that aligned the universe's first ripples. Is it possible that the very same large-scale gravitational gradients, the same cosmic hills and valleys that molded the infant universe, are also the source of our own local velocity today? This idea creates a breathtaking link between the global and the local. The dipole is not just our story, it is the universe's story. The direction we are moving and the axis imprinted at the beginning of time may both be pointing toward the same immense, underlying structure in the cosmos, a fundamental lopsidedness in the distribution of matter and energy that has shaped everything from the first light to our present path. We are not just observing a direction in the ancient sky, we are potentially moving along it, connected to the deepest architecture of reality by the silent, relentless pull of gravity. To test the reality of this cosmic whisper, scientists turn to the ultimate digital laboratory. Inside the world's most powerful supercomputers, entire universes are born, live, and die in a flash. These are cosmological n-body simulations, intricate virtual realities governed by the precise equations of our standard model of cosmology. Physicists program these digital realms with the same initial conditions we believe started our own cosmos, then set the laws of physics in motion, watching as billions of years of cosmic evolution unfold over mere days. Within these vast virtual boxes, dark matter clumps into halos, galaxies sparkle into existence, and a synthetic cosmic microwave background forms, a perfect digital echo of the real one. The goal is simple yet profound: to create not one, but millions of these simulated universes. By running this cosmic lottery over and over again, researchers can ask a fundamental question: how often does a feature as stark as the axis of evil emerge purely by random chance? The answer from these digital experiments is striking: a pronounced coordinated alignment across the largest scales, especially one that correlates with the simulated observer's local plane, is exceptionally rare. It is the digital equivalent of shuffling a deck of cards 1,000,000 times, and only a handful of times finding all the hearts in perfect numerical order. This statistical weight, drawn from 1,000,000 artificial skies, powerfully bolsters the case that the axis we see in our own sky is not just a fluke. Yet these simulations offer a second, more nuanced insight. They help us map the very boundaries of cosmic variance, the natural range of weirdness we should expect from a single random universe. They show us that while a perfect alignment is rare, our own universe often falls on the very edge of what the standard model predicts, residing in the outermost tail of the probability distribution. This refined understanding does not diminish the anomaly, it sharpens it. It tells us that while our cosmos obeys the rules, it consistently plays a melody that is just slightly off-key, a quiet but persistent signal that our story may still be missing a crucial verse. Perhaps the axis is more than a cosmic feature. It might be a fossil from before time began. Our current physics hits a wall at the very moment of the Big Bang, a point of infinite density where our equations break down. But theories of quantum gravity, like loop quantum gravity, attempt to peer beyond that veil. They suggest the universe did not emerge from a singularity, but from a great bounce, a transition from a previous cosmos that collapsed. In such a scenario, the pre-bounce universe could have possessed its own structure, its own unique geometry and directionality. That inherent anisotropy, a fundamental grain in the fabric of reality, would have been imprinted onto our new universe as it rebounded. The axis we see today could be the faint, stretched-out memory of that previous cosmic era, a scar from a time before our own. String gas cosmology offers another path to a structured beginning. In this view, the very earliest universe was a hot, dense tangle of fundamental strings. The dynamics of this vibrating gas are not perfectly symmetrical. Certain vibrational modes and windings could have preferred specific directions, creating a natural framework for anisotropy. As inflation stretched this stringy universe, it would have magnified that initial directional preference, freezing it into the cosmic microwave background for us to find. This transforms the axis from a puzzle into a potential portal. It could be our first and only observational window into the Planck epoch, that fleeting moment when the classical concepts of space and time as we know them were born from a more fundamental quantum reality. If true, this alignment is not a flaw in our universe, but a direct message from the moment of Genesis, a clue etched into the sky that could guide us toward the ultimate theory of everything. This secret buried in the cosmic background remains one of the most profound and stubborn puzzles of our time. From the first chilling detection of the axis of evil to its eerie links with the dark flow and the aligned light of distant quasars, this hidden direction challenges everything we thought we knew. It confronts the elegant simplicity of our standard model and questions the philosophical principle that we are not special. The evidence is a constellation of anomalies, a pattern of whispers that together form a question we cannot yet answer. Is it a ghost, a one-in-a-million statistical fluke amplified by our singular viewpoint in the cosmos? Or is it a signal, a crack in the foundation pointing toward new physics, a universe woven with a fundamental grain? Perhaps it is something even more extraordinary, a fossilized bruise from a collision with another universe in the vast multiverse. Each possibility carries staggering implications, redefining the nature of reality itself. Our journey to understand it is far from over. The next generation of observatories, with their armies of detectors, is already tuning its ears to the sky, listening for the echo of this axis in the polarized light of the infant universe. They will tell us if this is a true feature of the cosmos or a grand illusion. The universe is speaking to us through this ancient, fossilized light, and we are learning to listen more closely than ever before. The answer, when it finally comes, will not just solve a puzzle, it will rewrite our cosmic story. What do you believe this secret axis reveals? Share your thoughts on this great cosmic conundrum in the comments, and subscribe for more journeys into the deepest mysteries of space.